Hi guys, in this video we're just going to try and concentrate on the motion variables that we use for kinematics. In particular, we're talking about position, velocity, and acceleration, and how they relate to each other. And I want to make sure we also take a look at how the calculus plays into this and how each of these variables relate to each other. So simply, we have a position vector. That's just where an object is, right? And we kind of talked about in class that one way to compare how position changes is to compare it versus time. And that is what the derivative let us do. Okay, and when we write out the derivative like this, what we're talking about is how does position change with respect to time, right? And in this notation, d is not multiplying with r. This is just a calculus notation for how the numerator compares with the denominator. And in this case, the numerator is usually some sort of dependent variable. The denominator is some sort of independent variable. It doesn't have to be that way, but usually it is. And in this case, so therefore we're comparing, if I make a change in time, how does that influence a change in position? Which we then defined as velocity, right? And in this case, we're talking about instantaneous velocity. Velocity. That should say instantaneous. I ran out of room. As opposed to average velocity, right? When we're talking about average velocity, that would be something like this. We would sometimes use a net change using the symbol delta, and that would be like an average velocity. So something from endpoint to endpoint. Okay, so when we're talking about acceleration, now we're looking at how velocity changes. So if you're moving faster and faster, or changing which direction you're moving, any of these actually count as an acceleration. If you just look at the definition, if we write it like this, very similar to how velocity is written, we're looking at how acceleration relates to velocity, and that is just a change in velocity, right? So either changing in magnitude or direction. So, for example, sometimes you might not think of it this way, but if you are just going in a circle and you're going at a constant speed, you're actually accelerating because your velocity vector is constantly having to change direction. We'll take a look at that when we get to circular motion. For now, actually, what I would like to do is take a look at some graphs that compare position, velocity, and acceleration, and really kind of look at two specific situations. One is a constant velocity situation, and another is a constant acceleration situation. So let's start with the constant velocity. Okay, so what does constant velocity mean? That means your velocity should be the same all the time. And if velocity is the rate of change of position, meaning your constant velocity would have a constant rate of change of position with respect to time, you end up with a position versus time graph. And in this case, I'm going to use x just to simplify it in terms of keeping it one-dimensional movement. It's kind of weird to try and graph versus a vector, because a vector is multiple directions, can have multiple directions at once. But let's just look at x. Let's say you're just going along the x-axis, in this case a positive x-axis. And so if you have constant velocity, right, that means that at every change in time, you have the same change in position, right? And so then you'll find that the slope is your velocity. And if you look at the velocity versus time graph, it's constant, right? So we have a flat line, And if you look at what kind of acceleration versus time graph you have, it's 0, right? So it's down here, you got nothing. Okay, so it's kind of interesting to look at how each graph relates to each other, and what it reveals kind of is how the calculus relates to the physics. If you look at what velocity is to position, it's essentially like the slope. And so when you look at a derivative, it's kind of looking at a instantaneous slope, right? And so if velocity is the rate of change of time, and so it is the slope of, rate of change of position versus time, and so then velocity is the slope of that, then when you look at acceleration, acceleration is the slope of velocity versus time. So you can go like this. Slope, and then you get the slope here, right? So the slope of this graph is this graph, and the slope of this graph is this graph, at any particular given time. Let's see if we can find a relationship that goes the other way. In this case, we kind of inherently knew what constant velocity would lead to in terms of our position versus time graph, but let's kind of codify it, right? So think of a very simple situation like, let's say you're on the freeway and you're going 60 miles an hour, and you travel for an hour, and you wonder how far you've gone. Well, if you travel 60 miles an hour and you've traveled for an hour, then you've gone 60 miles. And so if you kind of write that as an equation, really looking at it in terms of the averages, let's not worry about instantaneous for now. But if you have a velocity, right, that is, again, that is your essentially your net change in position divided by some net amount of time that has passed. And if you rearrange this, you can get something like this. Right? Now, if you look at this graph, this one right here, and you look at this equation, this is kind of like the area under this graph, right? Because this is kind of like the height of this rectangle. Let's say you go for a certain amount of time, right? And you go for some delta t. Okay, so you go for some delta t, it's a constant velocity, and you kind of look at this rectangle here. That's essentially what this equation kind of works out to be, right? And so if you compare this one to this one, as time moves forward, right, the only dimension that's really changing here is the width. So as the width changes, this essentially becomes like a linear equation, right? V is the slope, which is the constant. It's like your mx plus b. This is like your m. And this is the independent variable that's changing over time. And then you can see that your dependent variable starts to go up in a linear fashion. And so essentially, this is kind of hinting at a particular operation in calculus that lets us reverse a derivative, right? So if a derivative is the slope and it's meant to go this way, we're kind of trying to find a way to go in the other direction, to go back. And it turns out that going backwards is effectively the same as finding the area under this graph gives this graph. There's some caveats to that, but for now, let's kind of run with that. So if I want to go this way, this is the area. Okay, so I get the area of this, and then that gives me this. It's a little different. And this operation in calculus we call the integral. Okay. So we take the derivative. This way is the derivative. Let me get rid of this guy. Okay, this way is the derivative, and then this way, derivative, integral. Okay, well, let's see if we can apply that logic over here to the acceleration. Can we take our acceleration and then give us a velocity? Well, the area under this graph is 0. There's no space under it. And so then that would kind of imply this should also be 0. But it's not quite, because when you look at this one, as this changed, this actually didn't tell us too much about the actual value over here. What it told us is how it should change, right? If you look at this right here, it's not x, the absolute value of, or the actual value of x. It only tells us how x changes. Okay, it only tells us how x changes. So the change in time tells us how position changes, but it doesn't tell us that your position started at 0, or it started at 10, or it started at 15. So this integral, or this area under this graph, actually only gives us the change in position. And so therefore, if we look over here, if the area under this graph is 0, that tells us that there's no change in velocity. Okay, so no change in velocity. Okay, we can kind of write that out. So we want to go this way, take the area, right? But this turns out to be no change. And that is another important aspect of the integral. And again, not worrying too much about how to calculate it with equations and so on and so forth, just trying to understand the meaning behind the words, or the meaning behind the math. So your slope is essentially your derivative. It is essentially talking about the rate of change. And the rate of change of your position gives you your velocity, and the rate of change of your velocity gives you your acceleration. And if you want to go the other direction, you want to go back. And you know your acceleration, that can tell you how your velocity changes. Not the actual value, but just how it changes. And your velocity can tell you how your position changes, but not the actual positions themselves. And you get that by looking at the area, right? So slope going this way, and then area is going the other way. This gives you the derivatives, and then this gives you the changes, the integral. All right, well, from here, let's take a look at constant acceleration then. So actually, let me get rid of some of this stuff. And I'm going to save this right here. So let's take a look at constant acceleration. Now this time, because we can kind of go from position to velocity and acceleration and the other direction as well, I actually want to start from the acceleration end. Okay, so let's say we have our constant acceleration. What does that look like? If you're looking at acceleration as constant acceleration, that means that this should be a flat line. Pretty, constant in that value. So how do we go from acceleration to velocity? And we had mentioned before that the area under this graph, let's say you go for some time period delta t, and that this area determines how your velocity changes. So following the logic from the constant velocity, then looking at this, if this is changing at a constant rate, right? Because again, you can kind of look at it like acceleration is change in velocity over change in time. And this is, if this is constant, then you can rearrange it to say that the change in velocity is acceleration times change in time. And this ends up being, since that's a constant and your time is just marching forward at a constant rate, then it's essentially a linear pattern. And like we said before, it doesn't tell us anything about what the initial velocity is. we don't know what this is. This could be anything. And so sometimes it'll be a given value, but regardless, we don't really know what that is. But we can calculate what this slope is, which is our acceleration. And we can also calculate some net change, some final velocity, and how it changed from some initial velocity. This is the delta V across some amount of time, delta T. Right? And really, actually, from here, how do we get to the position? Right? So the position versus time, at least the change in the position is going to be all of this area. All of it, right? So you get all of this, kind of color around the A, but it's all of that area. And so now you have a part of it that is the area of a triangle, and a part of it that is an area of a rectangle, right? So let's actually kind of look at that in terms of the math. I think that'll actually make it a little easier. So let me pull that aside for a second. And so let's break that down. So the change in the position should be the area of those two values. The triangle part, which is the change in velocity times the change in time. That's the triangle part. And then you also have the rectangular part. And so that's going to be something like this. Right? So there's two parts. This is essentially the contribution due to your acceleration, and then this part is the contribution due to the fact that your object may have already been moving. Right? Okay, so from here, we can see that delta V is kind of a variable in this case. It was actually a dependent variable dependent on this part, right? The acceleration. So how did delta V relate to acceleration? Well, we have this relationship. Oops, not delta A, just A times delta T, right? This was from, if it's a constant acceleration, then we don't really need to concern ourselves with the instantaneous anything. Everything can pretty much be the net change, right? And so this is just a rearrangement of that. And we can actually take this and plug it in. So we have delta x equals to 1/2 a times delta t plus v naught delta t. And we can actually kind of simplify that even to just delta x equals v naught delta t. This is the contribution to changes in position just due to the fact it may have already been moving, plus 1/2 a delta t squared. And that is where you're kind of getting that kinematic equation that we have in the textbook, right? Your change in position, if you have a constant acceleration, this is due to two parts, right? If you have no acceleration at all, you can see that this is the only term that will stay behind. And so if acceleration is 0, then you actually have the constant velocity situation. That's this part, right? That is the kind of equations we had for constant velocity. If you do have an acceleration, then this is the contribution from that acceleration. 1/2 a delta t squared. Now, for simplicity's sake, you don't have to have the delta t. It really just depends. Delta t is just considering the fact that there's some initial time that you're taking into consideration until some final time that you're taking into consideration. Most of the time, you will start from time equals 0. It's pretty much arbitrary. but maybe you have multiple events going on, and so you have constant acceleration only at a certain window of time, and so you're only taking into consideration the time that passes by in this constant acceleration situation. So what does this mean for what the position versus time graph looks like? Well, just looking at how change in position is a function of essentially change in time, right? Because v naught, that is going to be whatever your initial velocity is. It's a constant. It's something that you start with, and then it's not like you can change your initial velocity as time goes on. That is just what your velocity starts at. And here we're assuming constant acceleration, so this is also a constant. And so you can see this is just a quadratic equation with respect to change in time. So if we assume that this all starts at time equals 0, then as a function of time, it's essentially just quadratic. But again, this is how position changes with time. So if I go ahead and shrink this a little bit and bring this guy back, it's supposed to be quadratic, right? So I'm trying to find out what this graph looks like. So it could be quadratic, looking maybe something like this. And the initial position can be anywhere. We don't necessarily know where that is. We can't find that information out just by knowing the acceleration. So oftentimes in these kinds of kinematic problems, this is going to be a number that's given to you, and this is going to be a number that's given to you, or something about the description of the story problem or the setting will give that information to you. So for example, it may not explicitly tell you that the initial velocity is 0, but it will say something like a ball starts moving starting at rest. And so that is the information that you need to work your way backwards. Or it'll tell you it starts at the 30-yard line of a football field or something. In any case, you end up with a quadratic graph. So the slope of this, or not the slope, but how curved it is all dependent on the acceleration and the initial velocity. So that is kind of essentially how you can get your position versus time graph, velocity versus time graph, and acceleration versus time graph for a constant acceleration situation, right? So this is all for constant acceleration. So let's go ahead and recap the different situations that we have. We first started off talking about the different ways we measure motion. There's position, velocity, acceleration, and they're very interconnected. And a lot of the derivations that we went through here are not using calculus per se. It's kind of an introductory method of looking at the meaning behind the derivative or the integral. And if we actually had the calculus tools, we could use significantly more complicated types of motion. So as far as algebraically goes, and kind of using the graphs to find the relationships between acceleration, velocity, and position, we are really limited to just constant velocity and constant acceleration. None of these graphs would work out if we weren't just taking areas of rectangles and triangles. If I had some really curvy shape for my acceleration or velocity, this would become very difficult to do just by finding areas or using algebra. Calculus provides the tools for finding the areas under those curves or the slopes of those if they're given the function. But for now, this is good enough. This is mostly what you'll see on the AP exam anyway, and anything relating to calculus is really just going to ask about conceptually how they are related through the calculus. Maybe they'll ask about how to do it if you're given a function, but you'll know by May how to do that from Calc AB or BC or whatever it is. So going back, you got your different variables under a constant velocity situation. It looks something like this. Your position is linear, and the slope of that is constant. That gives you your velocity, and so on and so forth. And then if you look at your constant acceleration graphs, you got that quadratic, and then linear, and then constant. One thing I do want to finish with in summarizing the equations, we kind of look at the equations that we have. We essentially have, this is really the main one, right? Delta x equals to v naught t plus 1/2 at squared. That gives you both constant velocity and constant acceleration, because in constant velocity, you pretty much just make acceleration 0. This only works if you have constant acceleration, right? I mean, I guess you can consider an constant acceleration of 0 still constant acceleration. But it only works if the acceleration is 0. A lot of times, students make the mistake of using this kinematic equation to find the position of something, or the change in its speed, and so on and so forth, under situations where, say, something is moving in a circle, and the acceleration is not constant. So maybe it's speeding up and going in a circle, or maybe it is being pushed and pulled by multiple things, and it's, again, if the acceleration is not constant, you cannot use this equation. Just to kind of complete the set of equations we have, we did also have this one. Don't forget this. That's useful. And actually, if you do some algebra, sometimes you have a problem where you're not given the time. So sometimes it's convenient to have an equation that relates, for example, position and velocity and acceleration without time. So actually, if we solve this equation for time, assuming constant acceleration, and we plug that into here, you get something like this. And for delta v, what I'm going to do is I'm going to actually write that out as the change in velocity, having some final velocity and some initial velocity. And actually write this out. And it turns out, if you do all the algebra out, you end up with something like this. Okay. And so this equation is pretty convenient sometimes. You just gotta look at the problem and see if time is a variable that you have some information about. If you don't have any information about time, but you know, say, it tells you that you're throwing a ball up, and so therefore you know it's under gravity, you know the acceleration, and you know how high it went, or maybe you know how fast it was thrown initially, or what kind of velocity it has at some point mid-flight, or some information that involves these variables, then you want to use this equation. If you try and use this equation, you might get stuck. I mean, it's all algebraic manipulation, so eventually you can solve for time, and eventually you'll come to the same conclusion, but this can save you time if you, or save you a lot of work if you run into a problem where you don't have to use, if you're not given information about time. So this equation is a primary kinematic equation, and so is this one, and so is this one. These ones are the main conclusion of this kinematics unit.